Hello, everyone. Welcome to Sleep Space. Tonight, we will talk about a question that quietly lingers at the edges of science and philosophy. Is the past still out there in the universe somewhere? You're here now, perhaps settling into bed, ready to let your mind drift. As you listen, allow the boundaries between memory, science, and speculation to gently blur. And if you're listening from somewhere special or at an unusual time, let us know in the comments where and when you're tuning in from. Let's begin by thinking about what the past really is. You might think of it as everything that's already happened, the world of yesterday, last year, or even just a second ago. We experience it as gone, fixed, and unchangeable. But from a physics perspective, the past isn't always so easily dismissed. In fact, some of the most accepted theories of time suggest that the past may still exist, somewhere. To begin to understand this idea, we need to talk about what time is in the first place. Most of us think of time as a river that flows in one direction, from the past through the present and into the future. We're always riding the current forward, and the past is left behind us like a shoreline that vanishes out of sight. But this intuitive idea is not actually what physics tells us. When Einstein developed his theories of special and general relativity in the early 20th century, he radically changed our understanding of time. In Newton's universe, time was absolute. It ticked forward like a giant cosmic clock, the same for everyone, everywhere. But Einstein showed that time is not separate from space, it's woven into it, part of a single four-dimensional fabric known as space-time. In this framework, time doesn't flow. Instead, it's like a dimension, just like the three dimensions of space: height, width, and depth. If you imagine space as a block or a map, time is another axis that stretches alongside the others. Past, present, and future are not flowing but coexisting, just in different coordinates of space-time. This is what gives rise to the concept known as the block universe. The block universe view is a direct implication of Einstein's theories. In this view, the entire history of the universe, every moment that ever existed or will exist, is laid out like a frozen landscape. We experience time sequentially, like reading a book one page at a time, but the whole book already exists. Every page, the moment you were born, the first moon landing, a star collapsing in a distant galaxy, is still part of the universe's structure. They're not erased by the passage of time. They still are, even if we are no longer able to experience them. To help understand this, think about someone looking at a mountain range. Each peak and valley represents a moment in time. You may be standing on one peak, which we call the now, but that doesn't mean the other peaks and valleys don't exist. They're still there, just not where you are at this moment. But if the past still exists in the structure of space-time, why can't we access it? Why do we experience only the present? This is where things get more complex. Some physicists suggest that our consciousness moves through time in one direction because of something called entropy. Entropy is a measure of disorder or randomness in a system. The second law of thermodynamics states that entropy always increases in a closed system. In simpler terms, things tend to go from order to disorder. Ice melts, glass shatters, and you can't unscramble an egg. This increase in entropy creates what we perceive as the arrow of time. Imagine you're watching a movie of someone dropping a glass. Played forward, the glass falls and shatters. Played backward, the shards magically leap off the floor and form a perfect glass in someone's hand. The forward direction feels natural because it aligns with increasing entropy. The backward direction feels wrong because we never see entropy decrease. Our psychological arrow of time, the way we experience it, is deeply tied to this thermodynamic arrow. But here's the twist. The laws of physics that govern particles and energy don't actually require time to move forward. Most of the equations work just as well backward as they do forward. This time symmetry in physics suggests that the universe doesn't have a preferred direction of time built into its laws. The direction we experience may be a result of conditions in the early universe rather than something fundamental. This raises a profound question. If the universe doesn't destroy the past, and time's flow is an illusion driven by entropy, could it mean that the past still exists in some real, physical way? Could you be sleeping tonight in a universe where your childhood, or the moment the pyramids were built, still occupies a place in the cosmic structure? Let's pause here and consider how we actually know about the past. Our memories, photographs, and history books are all records, traces left behind. Light from distant galaxies takes billions of years to reach us, so when we observe them, we're seeing them as they were in the past. In fact, everything you see is technically a glimpse into the past, because light takes time to travel. When you look at the moon, you're seeing it as it was about 1.3 seconds ago. The sun appears as it was 8 minutes ago. Some of the stars you see in the night sky may no longer exist, and yet their light continues to reach us, giving us a record of their past presence. This is not metaphorical, it's literal. The past is imprinted in the light, the heat, the structure of everything around us. So even if we can't travel to the past, traces of it are everywhere. The question becomes not whether the past still influences the present, it clearly does, but whether it still exists as a part of reality, frozen in time and just out of reach. Let's also look at time dilation, another consequence of Einstein's relativity. If you travel close to the speed of light, time slows down for you relative to someone who remains at rest. This has been confirmed by experiments with atomic clocks on fast-moving aircraft and satellites. What this means is that time is not a universal constant. It's relative to your motion and your position in gravity. This suggests that what you experience as now may not be the same now as someone else, depending on their motion and location. And here's where it gets stranger. Because time is relative, there is no single universal present. Two events that seem simultaneous from your perspective may not be simultaneous for someone else in motion. This leads to the concept of relativity of simultaneity, which further supports the idea that all points in time, past, present, and future, are equally real. Imagine two observers moving at different speeds. One might say two stars exploded at the same time. The other might say one happened before the other. And both would be correct from their own perspective. In this framework, there is no privileged observer. The universe doesn't say which moment is now, it just contains all of them. This undermines our everyday sense of time as something that flows universally forward, and it opens up the possibility that the past is not lost. It's simply located elsewhere in the space-time landscape. It's not behind us, it's beside us, just inaccessible from our current vantage point. Now, let's bring this back to your moment right now. As you lie still, your body slowly relaxing, your heart ticking in rhythm with the silence. It might comfort you to think that the past, your memories, your ancestors, everything you've experienced, is not gone. It may still be out there, written into the structure of the universe, like chapters in a book you've already read, but which still exist on the shelf. You may not be able to turn the pages backward, but those pages are not erased. As we move forward in this exploration, we'll dive deeper into quantum mechanics, the nature of information, and what cutting-edge theories suggest about time's true nature. But for now, let this thought settle into your mind like a stone sinking slowly into calm water. Perhaps the past is not something behind you, fading away, but something beside you, quietly existing, eternally still. If the past is still part of the universe, why do we feel it slipping away? Why does it seem so unreachable, like something we've lost instead of something we're still connected to? To answer that, we need to turn to one of the strangest and most mysterious frameworks in physics: quantum mechanics. Quantum mechanics describes the behavior of particles at the smallest scales: atoms, electrons, photons. Unlike the predictable world of classical physics, the quantum world is built on probabilities. A particle doesn't have a definite position or velocity until it's measured. It exists in a state of potentiality, a cloud of possibilities, until that cloud collapses into a single outcome when observed. This is what we call the wave function. The wave function isn't just a convenient mathematical tool, it's the most complete description we have of a quantum system, and it evolves smoothly over time according to the Schrödinger equation until measurement happens. Then it collapses. But here's the mystery: what counts as a measurement, and what actually causes the collapse? One interpretation, the Copenhagen interpretation, says that the act of observation by a conscious observer causes the wave function to collapse into a definite outcome. But this leads to an unsettling implication that the universe exists in a haze of probabilities until we look at it. That the past too may not become fully real until it's recorded or remembered. Another interpretation is the many worlds theory, proposed by Hugh Everett in the 1950s. This interpretation says the wave function never collapses at all. Instead, every possible outcome of a quantum event actually happens in a branching multiverse. Each possibility unfolds in a different timeline, creating an endless tapestry of alternate realities. If that's true, then the past is even more complex than we imagined. Not only might it still exist, it may exist in countless variations. In one version of your past, you turned left instead of right. In another, a conversation lasted a few minutes longer. Each branching point creates a new thread in the fabric of reality, and all of them are just as real as the one you're in now. But here's what matters for our question. In both the Copenhagen and many worlds interpretations, quantum mechanics doesn't erase the past. It encodes it. The entire system, every particle, every interaction, remembers where it came from. That information is never truly lost. Even in the chaos of quantum uncertainty, there's a deep consistency. The past must still be there, written in the wave function of the universe. Yet we don't experience it that way. We experience the world as a steady unfolding of moments, each replacing the last. Why? This brings us to decoherence. Decoherence is a process by which quantum systems interact with their environment, causing them to lose their quantum behavior and appear classical. When particles become entangled with their surroundings, light, air, other particles, the delicate quantum superpositions collapse into apparent certainty. The world around us, filled with vast numbers of interacting particles, causes quantum effects to disappear on large scales. And what's crucial is this: decoherence doesn't destroy the quantum information. It just hides it. It smears it out across so many particles that we can't access it anymore. The past isn't gone, it's diffused, it's encoded in a trillion different ways, scattered into the environment, into the structure of matter itself. It's still there, just inaccessible, This is why some physicists think the universe is fundamentally deterministic at the quantum level. Even if we can't reconstruct the past perfectly, it's theoretically embedded in the present state of the universe. Every atom in your body carries with it a trail, a quantum fingerprint of where it's been, what it's interacted with, and how it came to be where it is. Let's step back for a moment. Think of time as a film reel. In the classical view, the film plays forward, and the frames behind us disappear. But in quantum mechanics, all the frames are still there. Each one is encoded in the structure of reality. They don't get erased, they just get entangled with everything else. This leads us to a strange but beautiful possibility, that the universe is not a river, but a recording, a hologram, not a broadcast. And every moment that has ever happened still exists, just hidden in the fine grain of reality. And if that's true, what does it mean for memory? Neuroscientists tell us that memory is not like a video we rewind and watch. It's a reconstruction. Every time you remember something, your brain reassembles the pieces based on chemical signals and neural connections. But even though memory is imperfect, it's real. It's evidence that your past happened. And more than that, it's evidence that your brain retains the structure of that past. But if we return to physics, we see that memory might not just be a function of biology. It might reflect a deeper truth, that the past exists not just in your neurons, but in the very fabric of the universe. Now, imagine a far future civilization with technology so advanced it could trace the quantum entanglements in every particle in your body. They might be able to reconstruct the exact state of your past, not just your memories, but your entire reality. The room you were in, the sounds, the light, the temperature, everything as it was. They wouldn't be time travelers, but they would be time readers. They could replay the past not by going back, but by decoding what the universe has always remembered. This isn't science fiction. It's a concept known in theoretical physics as unitarity, the idea that quantum information is never destroyed, only transformed. If unitarity holds true, then even black holes don't erase information. They just scramble it. Stephen Hawking once believed black holes destroyed information, but later revised that position, suggesting that somehow that information must survive, encoded in the radiation that escapes. Which brings us to the holographic principle. This is one of the most mind-bending ideas in modern physics. It suggests that the entire 3D universe might be a projection from a 2D surface, like a hologram. All the information about our reality, including its history, might be stored on this distant surface, possibly at the edges of the universe. If true, then not only does the past exist, it's embedded in the very walls of reality. Every moment, every action, every thought could be etched into the cosmic boundary, like carvings on the inside of a shell. We're living in the projection, but the full record is stored somewhere we cannot see. Is this just speculation? Not entirely. The holographic principle emerged from attempts to understand black holes and quantum gravity, particularly from the work of Gerard 't Hooft and Leonard Susskind, and it fits surprisingly well with string theory and the strange mathematics of anti-de Sitter space. Now let's ask a different question. If the past exists in some encoded, hidden form, why can't we go back to it? That question haunts every scientist who studies time. Time travel to the past remains one of the most tantalizing ideas in physics. And while no theory has yet allowed us to do it, several ideas suggest it might not be impossible. One is the concept of closed time-like curves, predicted in certain solutions to Einstein's equations. particularly those involving rotating black holes or wormholes. These curves loop back on themselves in time, allowing a traveler to return to a previous point. But they come with paradoxes. If you go back and change something, do you alter the present? Do you create a new timeline? Or do you simply fulfill what already happened? Some physicists argue that the universe forbids paradoxes, that any action taken in the past must be consistent with the future that follows. This is called the Novikov self-consistency principle. It suggests that time travel might be possible, but only in ways that preserve the timeline as it is. You couldn't change history. You could only become part of it. So even if the past is still out there, and even if we could reach it, we might find that it's not a place we can change, only observe. A fixed landscape, like a museum, we're allowed to walk through but not alter. But others propose that every time travel action creates a new branch of reality, that each change splits the universe, creating a new thread. In that case, the past would be more than a memory. It would be a multiverse of alternate versions, still alive in their own space-time paths. And that brings us back to our question: is the past still out there? From relativity, we learn that past events still have a place in space-time. They don't vanish. They remain part of the structure of reality. From quantum physics, we see that information is never lost. Even if we can't access it, it persists. From thermodynamics, we see that entropy increases, but the underlying state of the universe still contains echoes of what came before. And from cosmology, we see that light from the past still moves through space, carrying the story of ancient stars and galaxies across time. Taken together, these ideas suggest something remarkable. The past may not be something that slips away. It may be something that stays. We just lose the ability to return to it, to interact with it. But it remains written into the universe itself, like ink dried on the page. As you rest tonight, your body anchored in the present, your mind floating between thoughts, consider this: everything you've experienced may still exist, not just in memory, but in the fundamental weave of reality. Your first breath, your favorite moment, a warm glance, a falling leaf. These may not be gone. They may simply be elsewhere. Somewhere in the quiet structure of time, they may still be unfolding. We've looked at how relativity reshapes our understanding of time, and how quantum physics suggests the past might be encoded in the structure of the universe. Now, we take a closer look at one of the most enduring and mysterious questions in physics. If the past is still there, why does it feel so unreachable? Why do we experience time as flowing only in one direction? To explore that, we need to take a deeper look at entropy, the arrow of time, and the foundations of thermodynamics. At the heart of this discussion is something deeply counterintuitive. The fundamental laws of physics are time symmetric. That means they don't care whether time moves forward or backward. They work in either direction. If you were to reverse the direction of time in Newton's laws of motion, or even the equations of quantum mechanics, you'd get a universe that still makes perfect mathematical sense. Particles would still obey the rules. Stars would still form. Gravity would still pull. And yet that's not what we see in our daily lives. We see time moving from order to disorder. We see glasses break, but not unbreak. We remember the past, but not the future. We grow older, never younger. This directionality, this one-way flow, is what we call the arrow of time, and it's intimately tied to entropy. Entropy is a measure of how many possible microscopic configurations a system can have while still looking the same on a larger scale. A hot cup of coffee has low entropy when all the molecules are buzzing uniformly. Once it cools to room temperature, it has higher entropy. There are more possible arrangements of molecules that produce that result. The second law of thermodynamics tells us that in an isolated system, entropy tends to increase. That's why we age, why stars burn out, and why eggs don't uncrack. But here's the strange part. This law is statistical, not absolute. It reflects the fact that there are vastly more high entropy states than low entropy ones. It's overwhelmingly likely for entropy to increase, but not technically impossible for it to decrease. And that leaves room for wonder. What if the arrow of time isn't a fundamental rule of nature, but an emergent phenomenon? What if time flows from past to future only because the universe began in a highly ordered, low entropy state? That initial condition, known as the low entropy state of the early universe, is one of the deepest puzzles in cosmology. The Big Bang, far from being a chaotic explosion, was remarkably smooth and homogeneous. Everything was packed into a hot, dense state with incredibly low entropy. Why did the universe begin that way? No one fully knows. Some physicists believe it's simply a boundary condition, a rule we must accept. Others think it holds a clue to deeper physics we haven't discovered yet. But either way, the implication is profound. The reason we experience time as moving from past to future may not be a fundamental truth, but a product of where the universe started. This shifts our perspective. If the arrow of time is linked to entropy, and entropy depends on initial conditions, then maybe time itself is not something that flows, but something we traverse in a particular direction due to how things were arranged at the start. In that sense, the past is not gone, it's simply on the other side of a slope, and we're sliding down it. This brings us to another profound question. Is time fundamental, or is it emergent? Some physicists argue that time isn't a basic ingredient of reality at all, that it's something that emerges from deeper laws, just like temperature arises from the movement of molecules. In this view, time is a statistical illusion created by entanglement, thermodynamics, or quantum gravity. In fact, in certain formulations of quantum gravity, like the Wheeler-DeWitt equation, time doesn't appear at all. This equation describes the quantum state of the entire universe. It's a powerful and abstract idea. But here's the weird part. There's no time variable in it. The equation treats the universe as a static object, a whole, not something that evolves, but something that simply is. If this is true, then the entire line of the universe is like a sculpture, unchanging, eternal, with every moment baked into its shape. What we call the flow of time may be an illusion arising from our limited perspective, like a camera panning across a frozen landscape. You might ask, if time is emergent, then what does that mean for the past? If the flow is an illusion, does that mean all times exist equally and eternally? Some models say yes. In a timeless universe, there's no special moment called now. There is only the configuration of the universe at different points. The moment you were born is just as real as this one. It simply exists in a different part of the configuration space. You're not moving through time. You're a fixed structure in space-time, and your consciousness is the way that structure feels from the inside. In this view, your entire life, the joys, the losses, the quiet moments, is already etched into the universe. Not in sequence, but as a whole, a still, silent shape. You don't travel from past to future, you are the structure of all those moments, stitched together by the illusion of change. Let's go even deeper. In the field of quantum gravity, researchers are trying to merge general relativity and quantum mechanics into a single framework. One of the most promising approaches is loop quantum gravity, which suggests that space and time are made of discrete units, tiny loops woven into a kind of quantum fabric. In this model, space isn't continuous. It's made of indivisible chunks, like pixels on a screen. And time, too, may be quantized. It doesn't flow smoothly, but jumps in tiny increments. If that's true, then the past may not fade. It may be stored in those quantum loops, like frames in a cosmic animation. Another theory, called causal set theory, takes this even further. It proposes that space-time is built from a growing collection of discrete events, like dots on a page. Each new event is added to the structure, and the relationships between them define causality. There's no space or time, only events and their connections. The past is not a dimension, it's a structure. In causal set theory, the universe isn't a smooth block. It's a growing tree of events. And each branch, each node, carries the imprint of everything that came before it. The past isn't erased, it's part of the scaffolding that holds up the present. So many perspectives, and yet they all seem to suggest one thing. The past doesn't vanish. It's encoded, preserved, fixed. Now let's think about black holes, these mysterious objects where time and space behave in extreme ways. According to general relativity, a black hole is a region where gravity is so intense that nothing, not even light, can escape. But what happens to information that falls into a black hole? This question led to one of the biggest debates in theoretical physics. Stephen Hawking originally argued that black holes destroy information, that once something falls in, its details are lost forever. But this violated unitarity, the rule that quantum information is preserved. Over time, new ideas emerged. One was the holographic principle, which we mentioned earlier. It suggests that all the information about what falls into a black hole is stored on its surface, the event horizon. As the black hole emits radiation and eventually evaporates, that information is slowly released. Nothing is lost, just transformed. If this principle applies to the entire universe, and not just black holes, then everything that has ever happened is still encoded somewhere. Perhaps not in a form we can access, but in a form that still exists. Imagine every word spoken, every movement, every flicker of thought is etched into the cosmic fabric, not floating in space, but embedded in the mathematics that describe reality. Even now, in the darkness between galaxies, the light of ancient stars continues its journey. Some of that light began its path billions of years ago, long before Earth existed. And yet, it still moves, still illuminates, still reveals the past. When we look through telescopes, we see galaxies not as they are now, but as they once were. A kind of time machine made of photons. And you, lying there, are also a time machine. Your memories are records. Your atoms are ancient. Every particle in your body has existed since the beginning of the universe, recycled from stars, from dust, from other living things. You are built of history. So when we ask, is the past still out there? We're not just asking about physics. We're asking about our place in the cosmos, about meaning, about continuity. Because maybe what we really want to know is, did it all matter? Did those lost moments vanish into nothing? Or do they still echo, hidden, embedded, waiting? And physics, strange and incomplete as it still is, seems to whisper, it's still there. It always was. You cannot go back to it. You cannot hold it. But neither is it gone. The past may not be a memory. It may be a place. And though you cannot visit it, you are forever connected to it. Just like light crossing the vacuum of space, carrying the story of what once was, your existence carries the record of everything that led to now, and the universe remembers. Let's take a moment to consider how we actually study the past, not through memories or theories, but through light. Every second, the Earth is bathed in electromagnetic radiation from the universe. Some of it comes from stars nearby, only a few light years away. Some of it has been traveling for billions of years. That means the light you see when you look at the night sky isn't just light, it's information. It's the past, still arriving. This is most striking when we talk about the cosmic microwave background, or CMB. This faint glow, detectable only with sensitive instruments, is the oldest light in the universe. It's been traveling toward us since about 380,000 years after the Big Bang. Before that moment, the universe was a hot, opaque plasma where light couldn't travel freely. But when things cooled enough, light broke free and began to travel across the cosmos. That light is still arriving. The CMB isn't just ancient, it's uniform. It comes from all directions, forming a kind of shell around us, like we're at the center of a glowing sphere. But we're not at the center of the universe. Every point in space sees itself at the center of its own CMB. This symmetry tells us that the early universe was astonishingly smooth and homogeneous, and it preserves an imprint of the universe's structure when it was very young. When cosmologists map the CMB, they're not just looking back in time, they're seeing the past frozen in place. The patterns in that ancient light reveal the seeds of galaxies, the density of matter, and the way the universe has expanded over billions of years. That means part of the past is not just a memory or a theory, it's measurable. It's still out there in the form of ancient photons arriving one by one, and they don't just show us the past, they are the past. The photons striking the detectors of telescopes are the same ones released nearly 14 billion years ago. There's no gap, no delay, only distance. This is one of the most powerful arguments that the past isn't gone, it's only far away. In some cases, it's unimaginably far, but it exists in the structure of space, in the light that moves through it, and in the way gravity still bends around old stars and galaxies. Gravity, too, offers us a way to think about time. According to general relativity, gravity isn't a force in the traditional sense. It's the warping of space-time by mass and energy. When a planet orbits a star, it's not being pulled. It's following the curved path laid out by space-time itself. And this curvature doesn't just affect space, it affects time. This phenomenon is called gravitational time dilation. The stronger the gravitational field, the slower time moves relative to a weaker field. If you spend a day near the surface of a neutron star, a place of extreme gravity, you'd return to find that far more time has passed on Earth. This isn't science fiction. It's been measured with astonishing precision. Atomic clocks flown on airplanes tick slightly slower than those left on the ground. Clocks on satellites need to be corrected constantly to account for both their speed and their altitude. GPS wouldn't work without this adjustment. What this means is that time is malleable. It's affected by position, speed, and gravity. There's no universal ticking clock. Every location in the universe has its own rhythm, its own tempo, its own present. So when you ask, is the past still out there? One answer might be yes, and depending on your path through space-time, you might even reach it. Not directly, not like stepping backward through a door, but through warping, time dilation, or light delay, you might see events that happened eons ago, events still unfolding from the right frame of reference. And if that's true for distant stars and galaxies, could it also be true for us? This is where things become more philosophical than physical. You are here, now. That's your present. But someone far away, moving at a different speed, might consider your now to be their past, or their future. There is no single moment that is the present for the whole universe. The idea of simultaneity is not absolute, it's relative. This is one of the most unsettling and beautiful implications of Einstein's relativity. It breaks the concept of a shared universal present, and that opens the door to the block universe idea again. The notion that every moment in time still exists, but in different coordinates of space-time. Imagine a loaf of bread. Each slice is a moment in time. You're moving through the loaf, slice by slice, experiencing a sequence. But the whole loaf already exists. You just can't see the other slices from where you are. This analogy isn't perfect. Time isn't a spatial direction, but it captures something important. The idea that the past isn't erased. It's just not accessible. At least not in the way we typically think about access. But what if it were? Let's return to the idea of information. One of the most important principles in modern physics is the conservation of information. The idea is that the universe keeps track of everything. Even if something is destroyed, like a star collapsing into a black hole, the information it contained isn't truly lost. It might be scrambled, transformed, or hidden, but it still exists. This principle underlies our confidence in the reversibility of physics at the microscopic level. Even if we can't reverse the arrow of time ourselves, the laws of physics allow for it. And that means the past is not just a story, it's a configuration, a set of coordinates, a possible reconstruction. Some researchers have proposed theoretical machines that could reconstruct the past based on current information. These are called past hypothesis machines. They would analyze the present state of the universe down to its finest detail and, using the laws of physics, run the equations backward. In theory, this could reconstruct a past configuration that led to the current one. But there are limits. Chaos theory tells us that small changes in initial conditions can lead to vastly different outcomes. This is known as sensitivity to initial conditions, or the butterfly effect. In systems that exhibit chaos, even the tiniest uncertainty can grow exponentially. That means reconstructing the past with perfect accuracy would require perfect knowledge, something that may be fundamentally impossible. But still, the idea lingers. If the past left its fingerprint on the present, and if we can read that fingerprint clearly enough, maybe we can see it, not metaphorically, but literally. Maybe it's not about traveling back in time, but decoding what time has stored. Now think about your own life, your memories, your stories, your cells. All of them carry traces of the past. Every breath you take contains atoms once breathed by others, perhaps centuries ago. Every particle in your body has a history. Nothing is created from nothing. You are made of time. And what about your consciousness? Does it move through time, or is it a pattern that exists across time? Some theories of consciousness suggest that awareness is not bound to a specific moment, but arises from patterns, networks, information, structure. If so, then your conscious experience might be the product of a particular arrangement of matter and energy, a configuration that exists in one slice of the universal block. If that's true, then your past selves, The child you once were, the version of you watching a sunset years ago, aren't gone. They still exist in their respective configurations. You're just not experiencing that slice right now. But it's still there. Still real. Still part of the universe. This isn't wishful thinking. It's the natural consequence of many mainstream theories of time and physics. It challenges our everyday experience, but it aligns with what the mathematics tells us. We can't yet access these other slices. We can't jump backward or revisit old moments. But maybe we don't need to. Maybe knowing that they're still out there, preserved in the structure of the cosmos, is enough. Maybe that's a kind of immortality, not in a spiritual sense, but in a physical one. Because if the past is still real, then everything you've done, everything you've felt, everything you've been, is still part of reality. Not dust, not illusion, structure. The past is still out there, written into the texture of the universe, waiting in silence, carried in light, hidden in gravity, encoded in atoms. The past is not a shadow, it's a presence, a dimension we can't revisit, but that never disappeared. And even if no one ever sees it again, even if it's inaccessible, its reality remains. Not because we remember it, not because we believe in it, but because the laws of the universe do not forget. If we accept that the past is not erased but simply relocated, still present in the fabric of the universe, then we must ask what kind of universe this truly is. What kind of reality allows the past to remain? One possibility is that the universe is fundamentally timeless. This is a radical idea. We usually assume time is essential to reality, that it flows, marks events, and causes change. But some physicists suggest that time is not part of the most fundamental description of nature. Instead, time might emerge from something deeper, something more abstract. In quantum mechanics, time is treated differently than space. Space is an operator, a thing we measure. Time, by contrast, is a parameter. It sits outside the equations, acting like a background clock that tells particles when to evolve. But when we try to combine quantum mechanics with general relativity, this difference creates a problem. General relativity treats time as dynamic and flexible. Quantum theory treats it as fixed and absolute. In attempting to reconcile these two, we reach something strange. In many candidate theories of quantum gravity, particularly the Wheeler-DeWitt equation, the concept of time disappears altogether. This equation is meant to describe the quantum state of the entire universe. It doesn't include time, it's a timeless equation. What does that mean? It suggests that, at the deepest level, the universe doesn't evolve. It simply is. All events, past, present, future, are part of a single, unchanging quantum state. This state contains everything that has happened, everything that will happen, and everything that could happen. Our experience of time comes from the way we move through that state. This is where consciousness enters the picture. Your conscious experience is sequential. You feel like you're moving through time, one moment at a time, always forward. But what if this sequence is not a flow through an objective timeline, but a change in perspective as you shift through different parts of a static structure? Imagine a reel of film. Each frame is a moment. The reel itself doesn't change, but as you watch it, you experience motion and story. Your consciousness might be doing something similar, moving across fixed moments, creating the illusion of flow. In this view, the past still exists because it never stopped existing. Every moment you've lived, every scene of your life, still resides in the structure of this timeless universe. and your awareness, like a needle on a record, plays one moment at a time, giving rise to your sense of now. This doesn't mean you're an illusion. It means your experience of time is emergent, real, but not fundamental. It arises from something deeper. And this raises profound questions. If all moments exist equally, what distinguishes the present from the past? Why are you aware of this moment and not another? Some theories suggest that consciousness is tied to entropy. Your sense of now corresponds to a point in the universe's entropy curve, a moment when information flow is maximized. Others argue that consciousness simply samples the universe one moment at a time, in ways we don't yet understand. But either way, this suggests that the past is not lost. It's not something you leave behind. It's something you move through or move away from without erasing it. Let's take a step back and look at what we know. According to relativity, all events in space-time are equally real. There's no objective now that slices through the universe. There's no cosmic clock ticking everywhere in sync. Instead, there are countless different nows, each tied to a different observer. This is called the relativity of simultaneity. It means that whether two events happen at the same time depends on your motion. If you're standing still, you might see two stars explode at the same time. If you're moving quickly, you might see one explode before the other, and both observations are correct. This breaks the idea of a universal present. It supports the block universe model, a space-time where all events coexist. From this perspective, the past isn't something behind you. It's just somewhere else in the block. It's still there, unchanged, untouchable, but real. And then there's quantum entanglement. Entanglement is one of the strangest phenomena in physics. When two particles become entangled, their properties are linked, no matter how far apart they move. If you measure one, you instantly know something about the other, even if it's on the other side of the galaxy. This doesn't allow for faster-than-light communication, but it suggests something deeper, that the universe is fundamentally connected across space and time. That information is not localized, but woven into a web that spans the whole cosmos. Some interpretations go further. They suggest that entanglement is not just a feature of particles, but the very fabric of space-time itself. That space and time arise from patterns of entanglement. If that's true, then every particle, every interaction, every past event leaves a trace in the structure of the present. Not just metaphorically, but physically. That means the past isn't a memory. It's part of the entanglement network. It shapes the present not as a shadow, but as a foundation. And the present, in turn, shapes what we perceive as the future. Now consider a thought experiment proposed by Julian Barber, a physicist who advocates for a timeless view of the universe. Barber suggests that what we think of as motion and change are really jumps between different nows, distinct configurations of the universe. These configurations are called time capsules. Each one contains records, structures, patterns, and arrangements that imply a history. Your brain remembers the past, fossils record evolution, light records the birth of stars. But these records don't prove that the past existed. They exist only in the present configuration. They create the illusion of a continuous timeline, even if only the current configuration is real. But now imagine something more radical, that all these configurations exist. Not just the one you're experiencing now, but every possible one, all the nows, every time capsule, every moment you've ever lived. They all exist equally and eternally. You only experience one at a time, but they're all part of reality. In that view, the past is not a ghost, it's not a trail, it's a place. Not a place you can walk to, but a place that still exists. This isn't just a poetic idea, it follows from some of the most serious theories in physics. It's supported by relativity, it's not contradicted by quantum mechanics, and it may be the only way to reconcile what we know about time with what we experience. So what does that mean for us? It means your childhood still exists. Somewhere in space-time, it's still happening. You're still learning to walk. You're still looking at the sky for the first time. Those moments are real, not in memory, but in physics. It means that lost loved ones, old homes, forgotten days, they haven't vanished. They've only shifted out of view. You can't return to them, but they haven't ceased to be. And maybe that's what we really want to know when we ask whether the past still exists. We want to know whether what we've lived still matters, whether the things we've done still echo, whether the moments we loved are still part of the world. And physics, strange and cold and beautiful, says yes. They still are, not because we remember them, not because we long for them, but because the universe doesn't delete. We've seen how the universe may be timeless, how all moments could coexist, and how the past might remain eternally encoded in the cosmic fabric. Now let's focus on one of the most fascinating intersections of physics, information, and the nature of the past: black holes and information theory. Black holes are often called the ultimate prisons of the universe. Their gravity is so intense that nothing, not even light, can escape once it crosses the event horizon. For decades, physicists debated what happens to information that falls into a black hole. Stephen Hawking's early work showed that black holes emit radiation, now known as Hawking radiation. This radiation causes black holes to slowly evaporate over vast timescales. But Hawking initially concluded that the radiation was random, meaning that information about anything swallowed by the black hole would be lost forever. This conclusion was troubling. It violated a cornerstone of quantum mechanics, the principle of unitarity, which says information cannot be destroyed. Losing information would mean that quantum mechanics breaks down at black holes, an alarming prospect for physics. This paradox sparked intense debate, called the black hole information paradox. Over the years, physicists proposed various resolutions. One of the most compelling ideas involves the holographic principle, which suggests that the information swallowed by a black hole is not lost, but stored on its event horizon. According to this principle, the surface area of the event horizon encodes all the information about the matter inside. The black hole's boundary acts like a two-dimensional hologram, storing a three-dimensional record of everything it has absorbed. If the universe itself follows a holographic principle, then information about every event, every particle, and every interaction is stored on a cosmic boundary, perhaps the edges of the universe, or in the fabric of space-time itself. This suggests that the past, even when seemingly swallowed by extreme phenomena like black holes, is not lost. Instead, it is preserved, though often scrambled beyond our current ability to decode. Think of it as a cosmic hard drive, storing every file ever created, though encrypted and dispersed across unimaginable scales. Another breakthrough came from the idea of quantum error correction codes. Physicists found that the way information is encoded on black hole horizons resembles the error-correcting codes used in computer science. This means the universe might be protecting its information, ensuring that even if the physical substrate changes, the information survives. This is reassuring. It implies that, at a fundamental level, The universe is a trustworthy archivist. It keeps the record of all that has been. But what about the information encoded in the rest of the universe? What about the past that we experience in everyday life? Every particle in your body, every photon in the light around you, every molecule in the air carries an imprint of its history. This imprint is a record, one that's distributed and entangled with countless others. Information theory tells us that the universe is like a vast, complex network of information processing. Every interaction changes the state of the system, spreading information, and every state encodes what came before. In this way, the present moment is a composite of countless past interactions. Your cells know their own histories. Your memories are physical changes in your brain, patterns of synaptic connections that encode experiences. In principle, if you had perfect knowledge of the present, down to the tiniest particle, you could reconstruct the past. You could run the clock backward on the universe's evolution. This is called time reversal symmetry. But in practice, this is impossible. Because of chaos and the vast complexity of systems, even tiny uncertainties grow exponentially. That means the past is effectively hidden from us. However, the key word here is effectively. The information is not gone. It's just so entangled, so spread out, that no physical observer could ever gather it all. This leads us back to the arrow of time. Entropy grows because information about the past is encoded in a highly ordered way that becomes more scrambled over time. So the past is still out there, in the information carried by particles, in the waves of radiation streaming across the cosmos, in the structure of matter itself. It's not just a memory or a story, it's physics. And the universe is, in essence, a vast cosmic memory bank. Now consider cosmic background radiation again, the relic light from the early universe. This radiation is a snapshot of the universe's infancy. It's a record of a time when matter was almost uniformly distributed and conditions were remarkably simple compared to today. Scientists study tiny fluctuations in this background to understand the universe's evolution. Each pattern is a fossil, a clue, a preserved record of ancient times. That means part of the past is literally still shining toward us, carrying information across billions of years. We are living in a universe that preserves its history. It does not forget. This isn't a comforting metaphor, it's a scientific reality. What does this mean for you? It means that your past, your experiences, your actions, your existence may still be encoded in the cosmos, not just in your memories or the stories of others, but in the physical state of the universe itself. Your atoms are ancient, recycled from stars that exploded long before Earth existed. They carry the history of cosmic events. Your body is a walking archive of the universe's past. And perhaps consciousness, that mysterious awareness, is a way of accessing and interpreting these records. We have been exploring how the past may be preserved in the universe's structure, encoded in information, and entwined with the fabric of space-time itself. Now, let's look more closely at quantum mechanics, the fundamental theory describing the behavior of particles at the smallest scales, and how it relates to our question about the past. Quantum mechanics is unlike any other theory. It is probabilistic and counterintuitive, predicting that particles exist in superpositions, multiple states simultaneously, until observed or measured. This leads to what's called the measurement problem. How and when does a quantum system choose a definite state? At first glance, this may seem unrelated to the question of whether the past still exists, but it's deeply connected. The wave function, which encodes the probabilities of a system's various states, evolves smoothly and reversibly according to the Schrödinger equation. This evolution is time-symmetric. It works the same forward or backward. So, in principle, the quantum state of a system contains the information needed to reconstruct its past. But the moment of measurement, the so-called collapse of the wave function, appears irreversible. After a measurement, the system is found in one definite state, and the superposition seems to vanish. This introduces an asymmetry, a direction to time. How does this relate to the persistence of the past? One interpretation of quantum mechanics, called the many worlds interpretation, offers a compelling answer. It suggests that the wave function never truly collapses. Instead, all possible outcomes occur, each in a separate, branching universe. Every event spawns a multitude of parallel realities. In this view, the past isn't just out there in one timeline, it exists in many. Every possible history, every outcome, is real somewhere. This means that the past is not lost or overwritten. It is preserved in the vast multiverse. But the many worlds interpretation is just one perspective. Another approach focuses on decoherence. Decoherence describes how interactions with the environment cause quantum superpositions to appear to collapse, producing classical outcomes. It explains why we don't observe quantum superpositions in everyday life. From this perspective, the past is preserved in the environment as records. These records are physical imprints, photons scattered, molecules disturbed, that encode the history of interactions. In other words, the environment acts as a witness, continuously recording the universe's history. These records are stable and difficult to erase, preserving the past in countless redundant copies. This concept, called quantum Darwinism, proposes that the classical world emerges from the quantum substrate, because only certain information survives and proliferates through the environment. The past is preserved through this process of redundant encoding. Thus, the past is still out there, not only as a memory or story, but as physical information encoded throughout the universe. This idea connects with entropy and the arrow of time, as we discussed earlier. The proliferation of records contributes to increasing entropy and the directionality of time. Now consider the idea that the universe itself is a quantum computer, processing information through entanglement and decoherence. If the universe is fundamentally informational, then all events, including the past, are encoded as data processed within this cosmic computer. The past is not erased. It is a stored data set accessible in principle. Moreover, some physicists propose that time itself arises from the processing of information. The flow of time corresponds to changes in information states. In this framework, the past is a stable informational record, the present a processing moment, and the future a set of potential outcomes. This perspective provides a compelling explanation for why the past feels fixed and the future uncertain. It also suggests that the past still exists, as a set of records encoded in the universe's quantum state. What about human memory? Your brain is a physical system subject to the same quantum rules. It encodes memories as changes in neural connections, physical states that persist over time. These memories are themselves records of the past embedded in matter and energy. In principle, if these records were perfectly preserved and accessible, the past could be reconstructed with great accuracy. However, the brain is also subject to entropy, noise, and decay. Memories fade and physical records degrade. Yet, on a cosmic scale, the information encoded in your memories contributes to the universe's overall record. This leads to a profound insight. While individual memories may fade, the information they represent is not truly lost. It persists in the physical traces left behind, in molecules, photons, and the cosmic background. So, when you wonder whether the past is still out there, part of the answer lies in understanding that your personal history is a thread woven into the vast informational tapestry of the universe. From photons that traveled billions of years to reach your eyes, to atoms recycled through generations, to the quantum states encoding your brain's memories, the past is everywhere. It's a physical reality, not just an abstract concept. Finally, let's revisit the question of time's flow. If quantum mechanics, relativity, and thermodynamics all point to a block universe or timeless reality, then the flow of time is a feature of our perception, not the universe itself. Your consciousness moves along a fixed timeline, experiencing moments in sequence. The past is not something you leave behind. It is a fixed dimension that continues to exist. It's like standing on a mountain ridge, seeing the entire landscape laid out. You move along the ridge, but the valleys and peaks you pass remain unchanged. So far, we have explored many perspectives on the nature of time and the persistence of the past, from relativity's block universe to quantum mechanics and information theory. Now let's widen our scope and consider cosmology on the grandest scales, the entire lifespan of the universe. What does the fate of the universe imply about the past? And what if the universe is cyclical, endlessly repeating its history? Current cosmological models describe the universe expanding since the Big Bang, with galaxies moving farther apart. The discovery of cosmic acceleration, driven by dark energy, suggests this expansion will continue indefinitely. If this scenario holds, the universe will eventually reach a state of maximum entropy, a heat death. In that distant future, matter and energy will be so evenly spread out that no meaningful structures remain. Time, as we experience it, would lose meaning. But this bleak end isn't the only possibility. Some physicists propose models where the universe undergoes cycles, phases of expansion followed by contraction, and then a new Big Bang, a cosmic heartbeat. In these cyclic or bouncing universe models, the past is not confined to a single era, but repeats endlessly, with each cycle resetting or transforming the cosmos. This introduces a fascinating idea. If the universe cycles eternally, then the past from one cycle might be preserved or encoded in the next. How could that happen? Some versions suggest that certain physical constants or large-scale structures survive the transition, providing a kind of memory from one universe to the next. Others propose that information is transferred through black holes or quantum gravitational effects. This means the past isn't just out there somewhere, it's woven into the fabric of cosmic renewal. There's a philosophical concept related to this called eternal return, famously discussed by Nietzsche. It suggests that everything repeats infinitely, every event, every life, every moment. While not a scientific theory per se, eternal return resonates with some cosmological ideas, especially those involving infinite time or cyclic universes. If true, then the past you experience might recur endlessly across cycles. Your experiences, choices, and memories would not be one-off occurrences, but part of an eternal pattern. Even if the universe is not cyclical, some theories consider the multiverse, an infinite collection of universes with varying physical laws and histories. In an infinite multiverse, every possible past could exist somewhere. Every variant of your life, every moment you remember might be realized somewhere else. This stretches the idea of the past beyond a single timeline, beyond even a block universe, into an unimaginably vast landscape of realities. But let's return to entropy, the arrow of time, and their role in shaping our experience of the past. Entropy is not just about disorder, it's about information. Increasing entropy means information about the exact microscopic state becomes more diffuse and less accessible. The low entropy beginning of our universe set the arrow of time in motion, enabling complexity, life, and consciousness. Some cosmologists speculate that entropy could reset during a cosmic bounce, allowing time's arrow to reverse or start anew. If so, the past from one cycle could become the future of another, or vice versa. This challenges our common sense but is consistent with the mathematics of some cosmological models. On a smaller scale, some physical systems exhibit time reversal symmetry or cyclic behaviors, like oscillating molecules or quantum systems in superposition. Such phenomena hint that time might be more flexible than we imagine, with past and future intertwined in complex ways. From the perspective of physics, the past may be not only preserved, but also relational. That is, the meaning and existence of the past depend on the observer's frame of reference, state, and context. This aligns with the relativity of simultaneity and the observer-dependent nature of quantum states. Now consider the human experience. Our memories create a narrative that organizes the past into a coherent story. We anchor our identities in that narrative, giving meaning to our lives. But if physics suggests that all moments coexist, that the past is still there, then memory is not just a psychological process. It's a reflection of a deeper, more fundamental reality. Your memories connect you to a vast, timeless structure of existence. They are bridges connecting your present self to the eternal landscape of moments that define you. Sleep, briefly mentioned at the start of our journey, plays a mysterious role here. During sleep, the brain consolidates memories, processes experiences, and perhaps samples different temporal perspectives. Dreams often blend past, present, and imagined futures, hinting at the fluidity of time in consciousness. Sleep might be the place where the boundaries between past and present soften, where time feels less fixed. Understanding sleep could offer clues about how our minds interact with the timeless universe. Ultimately, science is still unraveling these mysteries. But what seems clear is that the past, far from being lost or vanished, remains out there, in cosmic radiation, in quantum states, in the architecture of space-time. It is preserved, encoded, and accessible, if only in principle. You are connected to it. Your story is part of the vast cosmic tapestry. The past is not a shadow, but a dimension of reality. It remains out there, waiting. As we continue, let's explore some of the most cutting-edge ideas in theoretical physics. Concepts that challenge our very understanding of space, time, and reality, and that shed new light on the question of whether the past still exists in the universe. One such idea is emergent space-time. Traditionally, we think of space and time as the fundamental backdrop against which everything happens. But some physicists now propose that space-time itself is not fundamental. Instead, it emerges from more basic, non-spatial, non-temporal entities, patterns of quantum information. This idea arises partly from attempts to unify general relativity and quantum mechanics into a single theory of quantum gravity. Because gravity curves space-time and quantum mechanics governs the microscopic world, we need a framework where space-time can be created or destroyed by quantum effects. Several approaches, including string theory and loop quantum gravity, suggest that at the smallest scales, space-time dissolves into something very different, perhaps a web of entangled quantum bits or qubits. If space-time is emergent, then past, present, and future are features of this emergent structure. The past would be one arrangement of these quantum bits encoded in complex patterns of entanglement. One influential idea here is the holographic principle. The holographic principle posits that all the information contained in a volume of space can be described by information encoded on its boundary. In other words, our three-dimensional world might be a kind of hologram projected from a two-dimensional surface. This principle originated from studies of black holes and their event horizons. As we discussed earlier, the event horizon encodes all the information about the black hole's interior. If the universe itself is holographic, then the past is encoded on this boundary, like a cosmic hard drive storing every event, every particle, every interaction. What does this mean for the persistence of the past? It suggests that the past is not lost or erased, but encoded in a way that transcends our usual notion of space and time. This encoding is highly non-local, meaning information about events is spread out and intertwined across vast regions, making the past accessible in principle, even if not in practice. Moreover, recent work in the field of AD-CFT correspondence, a mathematical duality between gravitational theories in bulk space and quantum field theories on the boundary, supports the holographic idea. In this framework, the bulk is a curved space-time with gravity, while the boundary is a lower dimensional space without gravity. Information about what happens inside the bulk, including its entire history, is encoded on the boundary. This means that the universe's past is captured holographically, preserved in a timeless quantum code. If this is true, then the past isn't out there simply because it happened and is now gone. It is out there in a deeper, subtler sense, encoded on a cosmic surface that underlies all reality. This flips our common intuition. Instead of thinking of the past as behind us, out of reach, we can think of it as encoded everywhere, in a cosmic tapestry woven from quantum information. Now, you might wonder how this relates to your personal experience. How can your past exist in a cosmic hologram? How does it connect with your memories, your consciousness? This is an open question, but several researchers suggest that consciousness itself arises from quantum processes in the brain, or at least that quantum effects play a role in cognitive function. If consciousness is linked to quantum information processing, then your experience of time, the flow from past to present to future, might correspond to shifts in these quantum codes. Your memories, as physical patterns in your brain, are part of this quantum informational structure. In that sense, your personal past is encoded not just biologically, but also quantum mechanically. Moreover, if the universe is holographic and timeless at its core, then your past selves, the child, the adolescent, the adult you once were, are still present as quantum informational configurations within this hologram. You're experiencing one slice of this vast information network now, but the others still exist. This may sound abstract, but it is supported by some of the most rigorous mathematics in theoretical physics. And it offers a powerful answer to our question. Yes, the past is still out there in the universe, encoded in its fundamental quantum structure. Another exciting development is the idea of quantum teleportation of information across space-time. Quantum teleportation is a process where information about a quantum state is transmitted instantly from one particle to another, over any distance without moving the particle itself. This phenomenon relies on entanglement and classical communication. It's been experimentally demonstrated in labs with photons, atoms, and ions. If we extend this to cosmological scales, it implies that quantum information can be shared across space and time in ways that challenge classical intuitions. Could this mechanism allow for a kind of access to the past through the entangled fabric of the universe? This is speculative, but not impossible. It suggests the universe's quantum state is a complex, interconnected web, where information from past events remains woven into the present and future. In summary, current theoretical physics paints a picture of the past as a living part of the universe's quantum information structure. It is encoded holographically, preserved by entanglement, and accessible in principle through quantum processes. This challenges our everyday notions of time, memory, and existence, inviting us to see reality as a vast, timeless information network. And in that network, your past is still out there, as real and present as the stars. As we reach the conclusion of our exploration, let's bring together the many threads we've followed about time, the past, and their place in the universe, and consider what this means for our understanding of consciousness, memory, and even sleep. Throughout this journey, we've seen that physics challenges the everyday idea that the past is gone, that it is erased by the present moment or lost to time. Instead, the past appears to persist, encoded in light traveling across space, in gravitational fields, in quantum information spread through the cosmos. It exists in the structure of space-time itself, in the cosmic microwave background, in the entangled fabric of quantum states, and in the holographic encoding on cosmic boundaries. This persistence of the past isn't just abstract, it is deeply connected to how we experience reality. Our memories, the stories we tell ourselves, the records we keep, they are physical imprints of the past, but they are only part of the story. The universe itself is a vast record keeper. And now, let's consider sleep, a state where time feels fluid, fragmented, and mysterious. Sleep is essential for memory consolidation. During deep sleep, the brain replays and reorganizes experiences, strengthening neural connections that encode our past. Dreams blend fragments of memories, emotions, and imagination, sometimes collapsing past, present, and future into a single experience. This hints at an intimate connection between sleep and our experience of time. Sleep may allow consciousness to sample the timeless universe differently, offering glimpses beyond our waking linear perception. Some scientists speculate that during sleep, the brain explores different states of information processing, perhaps touching on timeless or non-local aspects of the universe's quantum fabric. Whether or not this is true, it's clear that sleep affects how we encode and relate to the past. Our sense of identity depends on memory and the continuity of experience. Sleep helps maintain this continuity, linking one day to the next. So, as you rest, your brain is quietly weaving the threads of your personal past into the tapestry of your consciousness. From a cosmic perspective, this daily cycle echoes the universe's vast, persistent record. Sleep is a microcosm of the timeless processes we see writ large in space-time. Now, what does it all mean that the past is still out there? It means that nothing truly disappears. Every moment you lived, every event that shaped you, every memory, every particle you interacted with, is preserved in the fabric of reality. You are part of an eternal structure, a vast block of space-time, quantum information, and cosmic memory. Your past selves, the child, the adolescent, the person in this very moment, are all equally real and existing within this timeless framework. They are not lost to oblivion, they remain waiting in the cosmic record. This view can be comforting. It suggests a form of permanence beyond physical death, not in a mystical sense, but in the physical, scientific sense that information is never destroyed. Your life, your story, your impact, all remain etched into the universe. This raises profound questions about meaning, existence, and our place in the cosmos. If the past endures, what of the future? Is it already written, coexisting in the block universe? Or is it open, a landscape of possibilities that will be shaped by choices and chance? Physics gives clues, but no definitive answers. This uncertainty is part of the beauty of existence. You are both a traveler and a creator of time. Your experience moves through the timeless landscape, forging the present from the past and shaping what is yet to be. Before we close, take a moment to reflect on this. As you rest tonight, as you sleep and dream, remember that your past is still there, not just in your mind, but written in the stars, in the light, in the quantum codes of the universe. You are connected to all that has been, and all that has been is still with you. Thank you for joining this journey through time, space, and consciousness. If this exploration sparked your curiosity, please like, comment, and subscribe to continue expanding your understanding of the universe with soft science. Sleep well, and may your dreams carry you through the timeless realms of existence.